Chapter 7, Number 32. Initially sliding with a speed of 4.1 meters per second, a 1.5 kilogram block collides with a spring and compresses it 0.27 meters before coming to rest. What is the force constant of the spring? Since they don't say anything about the ground having friction, and because that would make the problem undoable, we will assume that the ground does not have friction. So what we have here is some wall, and there is a spring attached. And attached to the spring is some little platform or something so that we can hit the spring, and incoming is this box with some mass and some initial velocity. And then once it hits, what acts on the box is, of course, the spring force pushing back. And we know, or we should know, or hopefully you will remember that we derived in class that the work done in either extending or compressing a spring some distance, s, so let's go to a ghost version of our spring, where we have compressed this by some distance s. The work done on the spring is 1/2 k s squared. That's the work done on the spring, so the work done by the spring would have a minus sign. It pushes back against the work done by the spring on the block. Work and energy, it's kind of careful, you have to be really careful about who you're talking about. We're talking about the work done on the block, and on the block, while it's sliding, the force of the spring is pointing that way. So it will do negative work, which is good, because what we know is that the total work is going to be delta k, and the total work is the work done by the spring, because that's the only force acting. So we're left with 1/2 little k s squared equals delta big K. Be careful of the k's as well for yourself and for my sanity. Please make sure we distinguish lowercase k's from capital K's when need be. We assume that when they say it compresses it 0.25 meters before coming to rest, so we know that at the end the kinetic energy is 0, and at the start the kinetic energy was 1/2 mv0 squared. And we have that minus sign because we're doing negative work. So then we can just equate them, and we can say 1/2 k s squared equals 1/2 mv squared. That's a really common result, and it's worth feeling some comfort that it shows up a lot. Notice the halves will cancel out, and we'll end up with k is mv0 squared over s squared, or 4.1, or, to do this right, 1.5 kilograms times 4.1 meters per second quantity squared over 0.27 meters quantity squared. Quick reality check here. We'll have meters canceling out. We'll have kilograms per second squared, or we can cancel 1 meter, and we'd have kilogram meters per second squared per meter, which is a Newton per meter, or units of force constant. So I'm happy with that, and then we just figure out the numbers. This ends up being 345.88 newtons per meter, and our sig figness is that we have only 2, so this is really 350 newtons per meter.